Hello all of you. Welcome to the 17th lecture in the course on analysis and modeling in chemical engineering. In the last lecture, we started talking about chemical reactors and we developed the mole balance for different kinds of homogeneous and heterogeneous reactors starting from the general mole balance equation. In today's lecture, we are going to get the design equations in terms of the quantity known as conversion that defines the extent of a chemical reaction. So, just to recap, this is where we are. So, we have developed the design equations for different kinds of reactor. For batch reactor, we assume that perfect mixing and we have a differential form for the rate of reaction given in terms of the number of moles of species J and the volume V. And we discussed how to do it for the case of a constant volume and variable volume of the reactor. And then we also have an integral form for the time taken. For a CSTR, we assume perfect mixing and we also typically assume steady state, not always, but typically assume steady state, and then we get a simple algebraic form. And for the PFR, we assume that we have plug flow conditions and we typically also assume steady state, and again we have a differential form and an integral form for the total PFR volume. For the packed bed reactor, we model it similarly as the plug flow reactor, but we replace V by W and Rj with Rj prime, and similarly for the integral form we replace V1 by W1 and minus Rj by minus Rj prime. And finally, the fluidized bed reactor is modeled as a CSTR. Again, we imagine or assume perfect mixing and we typically assume steady state, and then we have a equation very similar to what we had for the CSTR, except that we replace V by volume weight of catalyst and Rj with Rj prime, that is per unit weight of catalyst as opposed to per unit volume per unit time. Okay. So, we typically talk about the extent of reaction in terms of conversion in all kinds of reactor. So, just to demonstrate the idea of conversion, let us imagine you have general kind of a reaction like this. We have discussed this kind of reaction earlier when we discussed chemical kinetics, and let us assume that A in this case is the limiting reactant, and therefore, we are going to use that as the basis of calculation. In that case, I can divide this chemical reaction by A, small a, and then we have something like this, and I can define the conversion X as the moles of A reacted, the limiting reactant A reacted per unit moles of A fed. Typically, we can define the conversion for different species like XB, XC, XD and all that, but it is a common practice to define it for the limiting reactant. As long as we have only one reaction taking place, this definition of conversion is the standard. When we have more than one reaction taking place in the reactor, then we typically work in terms of concentrations as opposed to conversion, and we will take some examples maybe later, right. So, when you have a single reaction taking place, then we can define conversion like this. I will call it X. We can also call it XA if we want to also define XB, XC and so on, but I will express the concentrations of all the species in terms of a single X value, that is the conversion of reactant A, where A is the limiting reactant. Now, naturally, if you have a irreversible reaction, let us say A going to B, then it is very well likely that all the A or most of A gets converted into B, and therefore, the theoretical limit of the maximum conversion we can achieve is basically 1, that is complete conversion. 1 may not be attained in all the cases because we have a flow taking place, but for batch reactors that is not a problem, we can go for complete conversion, right. But nonetheless, the theoretical limit is X max equal to 1 for a irreversible reaction. However, for the irreversible reaction, we can only go until the equilibrium conversion Xe, because once the forward reaction go until a certain extent, the reverse reaction is going to basically start, and then the equilibrium is defined as the rate of the forward reaction being equal to rate of backward reaction. So, it is highly unlikely or almost impossible that we can get equilibrium conversion is equal to 1. That pretty much means the reaction is irreversible anyway, right. So, when we have a reversible reaction, then this x max cannot go to 1, it can go to a maximum value that is defined as the equilibrium conversion. So, now let me write the design equations that we have already obtained in the last lecture in terms of conversion, right. So, this is what we have obtained in the last class, and now if I look at the moles of A that is present in the reactor at time t, what is it going to be? It is the mole that we started with, that is Na naught, and the moles which are reacted has to be subtracted from that. And how much is reacted is basically given by the conversion. So, conversion is defined as moles of A reacted by moles of A fed. So, therefore, moles of A fed in this case is Na naught. So, moles of A reacted has to be equal to Na naught into x, right. And therefore, we have simply Na is equal to Na naught into 1 minus x by definition of conversion, right. Now, if I plug that in this equation that we have earlier obtained, so dNA by dt can be written, Na naught is a constant here, as minus Na naught dx by dt, and that is equal to minus Ra into V. And now, we can basically also write the integral form by simply doing the same thing here. So, earlier we had time is equal to something like this, but now Na corresponds to a conversion of x and Na naught basically corresponds to a conversion of 0, assuming that we started with only A to begin with. In that case, we basically have this new equation something like this, and that basically can be expressed as this by changing the limits of the integration. Okay, so just one thing to keep in mind here is dNA starting from this equation of Na is equal to Na naught into 1 minus x can be written as minus Na naught dx, and therefore, we get a minus sign right here. Okay. So, now basically we had both the differential form of the design equation and the integral form of design equation in terms of conversion as opposed to concentration or the number of moles. Now, I can do the same thing for a flow reactor, where instead of Na naught I talk about Fa naught, that is the molar flow rate that is coming into the reactor, and Fa naught is the moles of A fed per unit time. But again, by the definition of conversion, Fa naught into x is basically Fa naught, that is moles of A fed per unit time, into the definition of conversion, that is moles of A reacted by moles of A fed, that gives me moles of A reacted per unit time, right. If I subtract this quantity Fa naught x from Fa naught, what are we going to have is basically the definition of Fa, that is the moles per unit time leaving the reactor. Fa is equal to Fa naught into 1 minus x, compared to batch reactor where we had Na is equal to Na naught into 1 minus x. The only change is that we have changed this number of moles by the moles per unit time or the molar flow rate, right. Going further, if we want to express this in terms of concentrations, we can use the fact that my Fa naught is basically concentration of A naught at time 0, Ca naught, into the volumetric flow rate, because the concentration is moles per unit volume and volumetric flow rate is volume by time. So, if I multiply the concentration with volumetric flow rate, we get basically the molar flow rate. And for the incompressible liquids, we can say that there is no change in the volumetric flow rate, V is equal to V naught. And for gases, we typically use the notion of partial pressures as opposed to concentrations, and we can express whatever equation we get in terms of partial pressure as opposed to concentrations for gases by using the ideal gas law, right. Okay. So, now we can go ahead and plug that definition of conversion that we have obtained into the design equation. Earlier we had this design equation we have derived, and now we know that Fa is equal to Fa naught into 1 minus x. If I plug it in this equation, basically I get the expression of volume as a function of conversion. And what again has to be noted is whatever rate we are talking about is the rate inside the reactor, and since we assume it is perfect mixing, the rate is basically referring to the concentration at exit, because the exit concentration is same as the concentration inside the tank. So just to emphasize that that concentration in the tank is same as the exit concentration. Here I am mentioning that exit, but keep in mind that that is also the concentration inside the reactor. Okay. So going ahead, I can do the same thing for a plug flow reactor, and I can write the design equation in terms of conversion. And again, you may recall I did now a mole balance over a differential volume as opposed to the entire reactor, and we derived this particular relation, noting that Fa is equal to Fa naught into 1 minus x. We can write dFa as minus Fa naught dx, which is what I did here, and therefore the minus sign went away from there, and we got the equation in terms of the conversion, right? And the same is true for the integral form. Basically, Fa naught came out, and then we had a nicely looking equation in terms of conversion. What is to be kept in mind that this is valid to the length of PFR, where the conversion is x. So here the volume is a variable, right? So I can find the volume until which the conversion is x, right? So if I talk about the total PFR volume, then I am referring as some V1, which will correspond to some conversion x1. But until here, we can say we have some conversion x, and then we can go ahead and use this equation. If I simply replace V by V1 here and X by X1 here, then we are going to have the total conversion in the PFR. Okay. So, one of the standard ways or the textbook ways of finding the volume of a reactor for a given conversion and a given production capacity is the Levenspiel plot, right? Why is that important? Is because let us say I want to make a reactor for a certain process. In that case, if I have more volume, I am going to have more capital cost, right? Because I have to make a bigger reactor, right? I have in control the production capacity that defines the molar flow rate. So, for a given molar flow rate, that means a certain production capacity, I want to maintain the same conversion x to have the final concentration to be the same, but I want to minimize the volume, because minimizing volume will basically reduce my capital cost, right? And the choices I have in this case is, let us say, of a CSTR and a PFR. Now, you can look at the design equations we have derived for a CSTR and PFR, and what you will notice is if I do a plot of Fa naught by minus Ra versus x, and let us say the plot looks like this red line here, then the volume of CSTR you can see is given by this algebraic equation that can be written as Fa naught by minus Ra into x. And what is Fa naught by minus Ra? Is basically this part of the rectangle. This is my Fa naught by minus Ra, and the width of the rectangle is basically x. So, if I multiply the length by width, we get the area of this, and this area basically gives me the volume of CSTR. In the case of PFR, however, we are basically having an equation like this. Again, now we have Fa naught by minus Ra changing along the length. So, let us say at this particular point, we have some value of Fa naught by minus Ra. Let me call this some variable y. So, if I integrate this y over this entire length of curve for a given conversion x, I am going to basically get the volume of a PFR, right. So, for a PFR, the volume is the area under the curve, and for the CSTR, the volume required for the conversion is basically the area of the rectangle that I have just shown how we draw here, right. And now we can use the same idea again for heterogeneous reactor. I had modeled the packed bed reactor as a PFR and a fluidized bed reactor as a CSTR. All that will change, it will replace the volume by the weight, and will replace the minus Ra with minus Ra prime. Minus Ra, again to emphasize, was moles per unit volume per unit time, and minus Ra prime is moles by weight of catalyst per unit time. And now it is very apparent from this plot that the PFR, that is the area under the curve, is going to require lesser volume than a CSTR for a given conversion. Is that always true? In general, it is true only when the rate is basically a positive order reaction, right? Let me demonstrate this point. So let us say we have some kind of a power law relation. Minus Ra is k Ca to the power n, where n can be greater than 0 for a positive order reaction, which is more typical, and less than 0 for a negative order reaction, which is less typical, and is equal to 0 for a 0 order reaction. As long as the rate can be expressed by the power law relation, these are the three possibilities. Of course, the rate can be a more complicated function, as we have discussed earlier, but these are the most common possibility, right? So, now using the fact that my concentration Ca is Ca naught into 1 minus x, we can write minus Ra as k Ca naught to the power n 1 minus x to the power n, right. And now if I plot my minus Ra versus x, what is typically is going to happen is rate is going to decrease as the conversion is increasing, right. The reason being that in the beginning you have high concentration of reactants, which will give you a higher rate as long as it is a positive order reaction. Let us say for first order we have minus Ra is equal to kCa. So, we begin with a concentration of Ca naught, and the concentration will go down until it reaches Ca. So, in the beginning you have high rates and in the end you have a lower rate. So, minus Ra is going to basically decrease with x. How it decreases depends on the power n. But this is true only when this n is greater than 0. If n is less than 0, then my minus Ra by x is going to increase with x for n less than 0. Again, something like, let us say we have minus 1 order, then minus Ra is k by Ca. As Ca naught basically decreases and becomes Ca, in the beginning you have high concentrations that gives me a smaller rate, and at the end you have low concentration that gives you a lower rate, right. Now, if I use this assuming that Fa naught is constant, so Fa naught by minus Ra, keep in mind that minus Ra is coming in the denominator, is going to look like something like this. Again, the shape will depend on the value of n, but the nature is always increasing with x for a positive order reaction, and it will look something like this for a negative order reaction, right. And clearly for n greater than 0, the PFR, which is the area under the curve, will give me a smaller volume, but the same is not true for a negative order reaction. In this case, this is the volume of a PFR, but a CSTR volume is something like only this, which is less than the PFR volume, right. So, in general, for positive order reaction, a PFR will give you a lower volume, but for a negative order reaction, a CSTR will give you a lower volume, right. We can look at the case of n equal to 0. So, in that case, minus Ra is going to be something like minus Ra is equal to k. It is independent of concentration and therefore independent of the conversion. So, it will look something like this, and in this case we can imagine that Fa naught by minus Ra is also going to look like the same curve, and therefore, now it does not matter whether we have a CSTR or a PFR, right. To conclude, for n greater than 0, we have to prefer a PFR. For n less than 0, we have to prefer a CSTR, and for n equal to 0, it does not matter, we can use either a PFR or a CSTR. Now, we can also find the concentration of other species in the system. Again going back to the general reaction we started with, we can now write the number of moles of species J for the batch reactor as something like Na naught, which is the number of moles of limiting reactant A, into a quantity theta j, that is basically the ratio of Nj naught by Na naught, plus the stoichiometric coefficient nu j into conversion X, right? And for the flow reactor, we are going to simply replace Fn with F, so Nj with Fj and Na naught with Fa naught, and theta j accordingly is in terms of F as opposed to N, right? You can see why this has to happen. So in this example, let us say we begin with species A in the batch reactor. So we can have some initial number of moles Na naught, and the way we have defined the conversion, the change is something like minus Na naught X, right? And now for every 1 mole of A, B by A moles of B are getting consumed, right? So the change in B is therefore something like minus B by A Na naught X, and minus B by A is the stoichiometric coefficient of B. That is why we have this nu j term coming in the expression, right? And what is the starting number of moles of B? That is some Nb naught, and that is the reason why we have this theta j term coming in the equation, right? For the products, clearly the change is going to be positive. So we have plus C by A. C by A is now the stoichiometric coefficient of C, and D by A is the stoichiometric coefficient of D. And again we have initial number of moles Nc naught and Nd naught for C and D. If we have some inert in the system, which is very typical in many cases, let us say we are having some reaction requiring oxygen, but we supply air into the reactor because air is cheaper than pure oxygen. So in that case, nitrogen in the air and every other thing in the air becomes an inert. So inert naturally does not undergo any change. So whatever number of moles we start with, the same number of moles is going to be there. In that case, the change is going to be 0. So now we can write the total number of moles by summing over the number of moles of every species. And if I look at the change that has happened in the number of moles, the total change, I can sum up all of this and I can express the change as some variable delta, that is basically in this case defined as d by a plus c by a minus b by a minus 1, but in general it is simply the sum over the stoichiometric coefficient, which is again positive for the reactant and positive for the products and negative for the reactants. Okay. So going ahead, let me just tell you about few complications that may arise in whatever we have developed, right? And we may not have time to discuss all of them, but you should keep in mind of what else can happen in this case. The very first thing is, until so far we have discussed only a single reaction happening in the reactor, but that is not generally true. You can have multiple reactions. For example, the same reactant A can go to 2 products or more than 2 products, right? So this is an example of a parallel reaction, and this may have different rate constants and different order of reaction for the 2 reactions happening, right? And of course, one of them may be a desired product and other one may be the undesired product. So the goal is to probably maximize the production of one of that, right? So there is a notion of selectivity of how we can favor the desired product and so on, right? We can also have a series reaction, A going to B and then going to C. In that case, if I really wait long enough, we are going to form C, but if I do not wait long enough, then we are going to form plenty of B. Now the question is, how are the rates for these 2 reactions and what are the order for these 2 reactions, right? And again, as I had said earlier, in these cases, it is preferable to work in terms of concentrations. Again, the basic idea of mole balance remains valid, but rather than talking about the rate of the reaction, we talk about now the net rate of the reaction. For example, if I talk about the rate of consumption of A, since it is being consumed in both these cases in this example, and let us say both are first order with rate constant K1 and say K2, now the rate of consumption of A here is something like K1 Ca plus K2 Cb for first order reaction, right? In this case, again, we can write the rate of formation of B as something like K1 Ca, that is how it is formed, minus K2 Cb, that is how it is depleted or reacting, right? So we have to consider the net rate, and we have to also work with concentrations as opposed to conversions. That is simpler in that case, and we may take some examples. The next thing that is also important in reactors often, particularly for PBR in the gas phase, is the notion of pressure drop, right? What may happen is, let us say you begin with some pressure P naught, the pressure in the end is going to be some P, right? And in that case, you can imagine that the concentration, since they depend on pressure, earlier we have said that the concentration depend on pressure, there is going to be an effect of that pressure drop on the conversion, right? So, at least for packed bed reactor in gas phase, it is typically common to consider that. For liquid cases, it is possible to have a pressure drop, but the effect of pressure drop is lesser because the density of liquid does not depend that much on the pressure as opposed to a gas. But nonetheless, it has to be better to keep in mind whether you have any pressure drop in the system or not, and whether it affects the conversion in the system, right? In the PBR case, it is found that the pressure drop basically depends on the weight of the catalyst, and that has to be accounted there. The last thing which we have not considered is the heat effects, right? In most reactors, you need to basically have certain arrangements to control heating, right? So, you can have either an exothermic reaction that may keep on heating the reactor up, that is also not good, or you can have an endothermic reaction that anyway requires heat to be supplied, right? So, in those cases, we need to also consider the heating effect. More importantly, we have to look at how the temperature is changing along the length of the reactor, and for the gas phase reaction, again the temperature may affect the concentration, right? That is same is also true for the liquid phase, although the dependence is weaker. But more importantly, we need to basically incorporate this idea of energy balance into our reactor math, whatever we are doing, right? So, in the coming lectures, I will also discuss the energy balance for these kind of reactors, right? So, with that, I want to basically conclude here. In the next lecture, I will take some examples on the mole balance of the reactors, just to demonstrate whatever concepts we have learned until so far. So, with that, I want to stop here. Thank you.